Yeah, thanks. So today I want to share with you about this theory of function placement and chaining for NFV. So that's all of my talk. I'll first try to give some motivation and background, and then I'll talk about the models that we're going to develop in this work. And then I'll highlight some of our scheme, basically high-level idea about our scheme and analysis, and lastly present some results and conclusions. So what is NFV? So if you look at the classical network application, so for example, in here, that we have a let's say a path that we have to first go to the firewall and then some routers, and then go through some CDNs. Okay, so what happens is that we will ask the engineers to go to the data centers or the ISP data centers to install these type of hardwares. And later on, if the company is saying that, hey, I want to remove these type of functions, but instead I want to go to deep packet inspections services. So what happens is that you have to again ask the engineers to go into the data centers or to the ISP data centers to kind of replace all this hardware. But the thing is, if you look at a lot of these networking services that a lot of networking researchers are spending the time on, we really have a lot of different services. So for example, message routing, CDN, session border, control, line, acceleration, so on and so forth. So NFV basically is to aim to transform these network operators architect and operate their networks by change. And change can be incremental. So the idea basically is that instead of really fix the software and the services on the hardware, we kind of just virtualize it and create a software for each of these type of services. So for example, we can have a software for firewall, software for routers, software for DPI, and so on and so forth. But instead of pinning down on a particular hardware, we basically allowed some standard high volume servers. So the idea is that if you want to deploy some type of service, we can basically instantiate some of this software, some of this service into our servers, and when finished, we can basically deactivate all this type of service. Okay, so the idea is basically to map all these type of network services into what we call the software. Okay, so that we can easily deploy it. So what is NFV training? Okay. The thing is that services are basically composed by a number of sequential functions. So for example, a while ago, I showed the example that it has to go through a firewall and then a router and then a CDN. And virtual functions can be quickly, okay, at least in the framework of NFV, can be quickly instantiated or deallocated from servers. And then more importantly, we can do it online, okay? So this one actually is an example here. I have a user A, basically his path basically has to go to this customer premises equipment and then go to this deep packet inspection service before going out to the internet. On the other hand, server B basically his path basically has to go to this CPE and then a firewall and then a deep packet inspections, okay? But in here, as long as we can instantiate this software on different servers, okay, online quickly, we can basically do it. We don't have to ask the engineers to go to the ISP, to kind of remove the hardware and put in new hardware there. So there are many technical challenges for NFV. Okay, so for example, for given NFV functions, how do we identify these functions? How do we, efficiently compose these services based on some standard functions? How do we do the rate control and rate limits, okay, within the network when we have NFV? Okay, because if we don't do that, we can create a lot of congestions and packet loss. Where do we deploy these functions? Okay, do we deploy it? It can be large regions. Okay, so for example, for a lot of overlay networks, and deploy different functions. Okay, or I can deploy in data centers. Now, in this work, basically we focus on a specific problem on NFV. Basically, it's a function placement problem that is given a physical network. Okay, and given a set of service chains. Okay. And how can we do the placements? Okay, and in here we make a simplifications that we assume that is a homogeneous setting. That means that each functions take a unit cost. So let's dive into the model. The model basically is the following. We have a physical network. So we have a set of nodes and edges with link costs and server costs. So this example here, I have a set of servers, and each server basically can support so many functions. And there's also, there's a server capacity and so on and so forth. And we also have a set of service chains. So in here, example is that I have 3 service chains. The first one basically has 4 functions, A1, A2, A3, and A4. The second one, B1, B2, B3, has 3 functions, and so on and so forth. And our question basically is, given these network topologies, okay, with all the capacity and network constraint at edge cost, how can we place this type of set of network functions, okay, onto these networks? And the idea basically is that in here, given a set of service functions, when we consider the chaining requirement and the link cost, how can we place on the servers? And the functions can be placed on a single server, or 2 different functions. 2 different functions can be placed on the same server or different servers. Okay, so as to map our service chains. And the objective basically is for this function placement and service chaining is to minimize the overall cost. So before I kind of dive into the equations, so this is one example here. I have a very simple network. I have 4 nodes. And each of these nodes, so for example, in node 1, I have this C1 here. Basically, it's a capacity of node 1. So you can hear C1 is equal to 3 basically means that this server can support at most 3 functions. And I also have this C1, 2 here. Basically means that it's the capacity of link 1, 2, or from node 1 to node 2. So in here, basically means that it's 2. Basically means that I can only map 2 functions if 2 functions have to talk between server 1 and server 2. And on your right, basically, I have this Wij and Wi. Wi basically you can view that as a server cost. If I place functions in server I, okay, server 1, for example, then I will incur this cost of 22. And if my function has to go through server 1 and server 2, I have to, let's say, pay a cost for 58.8. So lastly, on your right, I have a service chains. I have 3 service chains here. The first one basically has 2 functions. The second one has 3 functions, and the third one has 3 functions. So in here, let me first define a term first. A configuration basically is one possible placement and chaining schemes for service change. Okay. So for example, here in my service 1, okay, service 1 L1, I have 2 functions, S1 and S2, and each functions can be placed in any of the 4 servers in my network. So altogether, I have 4 to the power 2, or 16 different configurations that I can test for service chain 1. And remember, right now I have 3 different service chains. Okay. And the cost for configuration PK, okay, so in here, for service chain 1, I have P1 up to P16, okay, and the cost for this configuration basically is, you can view that is, I can add up, if I use any servers, I have to include the server cost. If 2 functions have to go through 2 different servers, I have to add up the link cost. So this one actually is the cost for certain configuration for service chain K. And our objective basically is to minimize the overall cost. So the outer summation basically is to sum over all service chains. The second summation basically is sum over all possible configurations, because for each service change, I can place in any number of servers. Okay, and C sub KPK basically is the indicating functions. So I want to find the optimal configurations so that I can minimize the overall cost. So, for service chain K, there are, n to the power LK functions, where LK is the number of functions in service chain K, and CP KPK basically is some node chain K, it's a local configuration PK, so I can do that for pre-processing. Now, I also have different constraints. The first constraint basically says that for each service change, I have to select 1 feasible configurations. And another constraints that I have to consider is saying that for all the servers, okay, I can place whatever functions I want to, but it has to be less than or equal to the capacity of server I. Lastly, also, I can place whatever functions I want on different servers, but the thing is that the link capacity cannot be exceeded. Okay, so these are my constraints. So if you look at this one, actually, it's an integer problem. And there exist, if you look at the existing work, there are basically 2 approaches. One basically is a very greedy approach, and what I call the heuristic approach. That is, they just pick one particular service chain first, choose the configuration with the lowest cost, and update the server's capacity or subtract from it because you placed some function on the server already. So update the server capacity and link capacity, and then choose configuration for the next service change. Now, so this is kind of like a greedy approach, but the problem is that most of the greedy algorithm, okay, is that they're heuristic. Okay, we really don't know how far away from the optimal solutions unless we know something about the objective functions. Let's say submodular, monotone submodulars. Okay. Another class of approach basically is what they call the random rounding. Okay, that is, if you have a large service chain placement problem, okay, the real issue actually is the computations. So the idea basically is to relax the integer problem into a linear programming problem. Okay, so you can solve it in polynomial time. So that is, instead of picking a certain configurations, either you don't select it, or select it. You say that fine, I can relax it into integers, and I solve this linear problem to obtain these solutions. So this is what I call the fractional solutions. And for service chain K, basically you randomly select one possible configurations based on these fractions or based on this probability. Okay, so in other words, if one of the configuration has, the solution is 0.8, you select the configurations with probability 0.8. Okay, now, so that's one of the approach in the literatures. The problem is that if you look at these type of solutions, it's possible that the selected configuration may violate the capacity constraint, either the server capacity or the link capacity. Okay, and in other words, more importantly, this violation may increase if we scale up the network. Okay, so the networks that we want to deal with, usually they're very large and it composes of a lot of service chains. Okay, so what is our scheme here? Our scheme actually is quite simple. Okay, the idea basically is we first relax the integer problem into a linear one, similar to what people did in random rounding. We solve this linear problem and obtain the solutions, okay, the fractional solutions. But the key contributions of our work is that we try to review some of the intrinsic properties about these solutions. In particular, we basically shows that the number of non-zeroed configurations, okay, can be upper bounded. Now, why that is important? Because it basically reduces our search space and can help us to quickly come up with good solutions. Another one we can basically show is that the utilization of these selected configurations can be lower bounded. So again, it reduces our computations to find the good solutions. And this pre-select configuration with high utilization change can help us to find a pretty good solutions. And at the end, we can run this with a mean cost flow optimizations to further improve our placement. So, so the property one basically is saying that you can basically easily prove it. Assume that let's say all servers has a same. Assume that I pick the minimum a server that has a minimum capacity and the link that has a minimum capacity, and then basically you can show the number of active constraints is bounded. Okay, so that is kind of the high-level idea about how we can prove the property one. For property two, basically it's saying that given the result of property one, and we know that the total number of service chains is k, and we can get at least alpha k of them with utilizations no smaller than these fractions here, and where alpha can be any value between 0 and 1 is upper bounded by k. Okay, so in other words, the utility about these properties is that the violation we can bound the violations. Okay, so this is an example here. So in here are 5 servers. Each server assume that I can only host 2 functions, and I also have a label about the link cost and the link capacity. So for example, in here, the link between node 1 and node 2, you have 249 and 2. So basically means that the first number is the link cost, the second number is the link capacity. And let's say I have 2 service chains. Okay, one requires 4 functions, the other requires 3 functions. So they're heterogeneous service chains. I can use our method to solve the linear optimizations, obtain the optimal fractional solutions, and each node basically can host 2 functions. Okay, so in here I have 2 configurations here. So in here, if you look at the first row here, I have 4A and 4B. First 2 rows here basically means I have 3 functions. I use 3 functions. Also, what is 4A and 4B means? Because I have 4 basically means the server 4. I just kind of mirror it into server 4A and server 4B. So in here, basically, I say that I can use server 4A to place the first functions, server 4 again to place the second functions, and then server 1 to place the first another functions, and so on and so forth. Okay, and you can basically show that using our results, saying that at most I can only need to consider 10 configurations because they have non-zero utilizations, or probability of being selected is greater than 0, and at least alpha k of them basically has this utilization no smaller than this number here. Okay. Now, how can we place it? One thing we can do is we can find the maximum configuration set. However, for those of you, look at this maximum configuration set, you know that actually is a NP-complete problem. Okay, so we want to avoid that. Instead, we use this maximum configuration set is sufficient, so we can choose the first configurations, and we can, after we choose the first configuration for the first service change, I can use the remaining service chains of the network to place another service chains. So far we get this result based on two properties or two theorems of our paper. The question is, can we do a better job? Okay, actually we can do a better job because once we have these initial configurations, okay, we can map the remaining nodes 2A, 2B, and 3B into what I call the layer networks. Okay, and we can attach virtual source and virtual destinations there, and run what we call the mean cost flow optimization problem, which is basically the integer linear programming problem. So in here, I just want to highlight that before we run this mean cost flow optimizations, the total cost is actually 629. But if we after this refinement, we basically significantly reduce the cost to 463. Okay, so try to compare with some of the latest results. So this result actually is recently appeared in JSAC. The idea basically is to utilize, so basically, they use propose some greedy approach. Because the network configuration is very small, the optimal one is a total cost of 371. Our scheme actually is 463, okay? This paper actually is trying to mimic the greedy, so it's around 629, okay? So as you can see, our approach actually is much, much smaller than the current state of the art. Okay, and lastly, I just want to show you some simulation results. So this one basically says that I have 26 servers. Each one can, let's say, host 1 unit capacity. That means that 1 functions. And then mean cost between any 2 servers actually is randomly selected between 0 to 1,000. I have 8 service chains. Each one of them, I have 3 functions. And I try different configurations. So you have 1,000 instances. And the first one basically says that at most, I only need to find 32 non-zero configurations. Okay. Now, so you can see that actually in our experiments, we find out that, so this is the upper bound, but in our experiment, actually you see that after the 19 configurations, the cumulative distribution is already close to 1, right? So in other words, in reality, we use our algorithm, actually the search space is much smaller. Also, the second figure here basically shows the low bound on utilizations. Same thing here. So lastly, about this one, again, I have 26 servers. Each service change has 3 functions. And I do want to use what I call the weighted cost, which is the actual cost we have in our algorithm divided by the optimal integer cost. So that means that we do an exhaustive search, find out the optimal integer cost. So the best we can do, obviously, is 1, okay? And usually the actual cost actually is higher than the optimal cost, so the weighted cost can be greater than 1. Now, this figure here basically says that I plot the weighted cost. The minimum obviously is 1, okay? The y-axis actually is a cumulative distributions. The blue line here actually is our scheme. As you can see, most of our, because we try 1,000 instances, most of our scheme basically quickly converge to 1 with this type of cost, okay? So after 1.4 already is very close to 1. However, if you use the greedy scheme or carrot scheme, you can see that actually a lot of them, okay, has much higher weighted cost. Okay. The second figure here basically shows that the weighted cost and the cumulative distributions. Basically, what happens if you use the random rounding? Another state of the art. Basically, people use that in the current literatures. Now, one thing I want to highlight basically is that although they come with some solutions, but actually they violate the constraint. In particular, 85% of these 1,000 instances that we tried, they violated capacity constraints. Okay. So in conclusions, I want to say that our model basically uses a configuration to indicate the placement of service chains. The most important result is that the NFV chaining and placement problem, basically what we did is to map it, we can map it to an exponential number of mean cost flow problem, but we don't need to solve this exponential number of mean cost problem because we can find the upper bounds, okay? In fact, you only need to select a small number of map mean cost problems to find the solutions, okay? And we show the underlying properties of our problem, and we also take advantage of the good configurations and map it to a mean cost flow optimizations. Okay, and currently, actually, our work is supported by some company, and we actually right now is trying out the deployment in one ISP, okay, one operators, and in another company in our data centers, okay, just to place the NFV. Obviously, there are a lot of future work. So if you look at this problem, one thing you can say, hey, John, you have a network topologies, and then you have a set of service chains. But in reality, a lot of times, these service chains actually is dynamic, right? They can come in one at a time, okay, with heterogeneous service chains. If it's dynamically come in, what should you do? Okay, so right now, my students we are working on this type of problem. That's it.